Hello students, how are you? I hope you all are good. So today in this lecture we are going to discuss about one-dimensional element, right? So coming to one-dimensional element, we have to study about two different types. Like first one, we will study about bar element, and the second one is beam element. So in one-dimensional element, we have to go to bar element as well as beam element. So first we will start about bar element, and then we will go to beam elements, right? So what is this bar element? First we will see this bar element and beam element. What do you mean by this bar element and what is this beam element? So if you will see the difference between this bar element and beam element, see, suppose this is the cross section, right? So at what condition we will consider this as a bar, and what condition we will consider this as a beam? The condition depends upon the force. What type of force is acting on this member? Suppose we have a member. So what type of force will act on this member? That will decide whether the given member is a bar element or the given member is a beam element. So the condition is we can apply, basically we can apply two types of forces on this member. The horizontal force, right? Or vertical force. If we are applying the horizontal load on this member like this is the horizontal one. So if we are applying the horizontal load, then this member will be called as bar element. This will be bar element. But if we apply the vertical load, suppose this is the member, and if we are applying the load like this, suppose this is P, let's say this is P load, right? Then whenever the vertical load will apply on this type of member, then we will call it as a beam element. Now most of you have studied about the subject like strength of material, structural analysis. So whatever we have done the analysis for beam, in that beam what we have taken the loads like this only. Right? If you can remember, just recall, whatever the loads we have taken, that loads were vertical loads, not the horizontal load, right? If such loading are there on the same member, then we will consider that as a bar element. And if the vertical loads are there, then we will consider as a beam element. So almost the analysis is also same. Only the difference will be in the stiffness matrix. Remaining things will be almost same for analysis of bar element or beam element, right? So first we will discuss about bar element and then we will jump to beam element. So let's take an example of a bar element. So let's take a bar element. Suppose this is your bar element, and one side of this bar element is fixed, right? This is the fixed support. Why I am telling this bar element? Then obviously if I am saying this is a bar element, then I have to apply what type of loading? I have to apply horizontal loading. So let's take this is a load, right? Now a specification of this bar element, area of cross section is A. Second one, area of cross section is given, Young's modulus is E, and its length, let us take this is L. So these are the specification of this bar, that a load is acting, F load, that is horizontal. Obviously, then only we will call it as a bar, right? This is a bar element, talking about bar element. Area of cross section is A and Young's modulus is E. Yeah, one more question you can ask. Sir, you are saying this is a one-dimensional element, then why you are considering area of cross section? See, why we are considering this bar element or beam element as a one-dimensional element? Because as compared to its length, its thickness is very small, right? So if you will see its length, and this is the thickness, right? This is the thickness. So if you will consider, this length will be greater than the thickness of the element. If such condition follows, we will consider this as a one-dimensional element. even though we can find the area of cross section, length into thickness, but we will consider this as a one-dimensional element because the ratio of length is to thickness is very, very small. Means thickness is very, very small as compared to the length of the element. So we can ignore the thickness, right? So if you will remember the first unit, plane stress and plane stress condition, there we have discussed about something about thickness. Just go through that video, you will get to know each and everything. So here we are considering this as a bar element, or what type of element is this? One-dimensional element, right? This is one-dimensional element. So if you remember SM subject, then there we have a formula delta L is equal to PL upon AE. Here P is nothing, your F. So we will use this formula. If you don't remember also, so I am going to just, it will take within 1 minute. I will derive it. How, let's see how we are going to get this equation. And what is the use of this equation? Why I am taking this equation from strength of material for this case, bar element? Let us discuss that. So I hope everyone knows the stress. Stress is nothing, resisting force per unit area. So here obviously the case is the resisting force will be equal to the applied force only. So we will take this applied force per unit area. From here we can say this applied force will be equal to sigma times A, right? This stress times area of cross section, right? Now we can write this F is equal to sigma. From Hooke's law, we know, from Hooke's law, what we can say? Sigma will be equal to epsilon E times epsilon. What is this? From Hooke's law, we know stress is directly proportional to strain. So if you will remove that directly proportional, we will get Young's modulus. This is Young's modulus times strain. Sigma is equal to Young's modulus into strain. So we can replace this sigma by this E into epsilon. So we can write here E into epsilon into area, right? These all I am taking very basic things I am taking from strength of material. Now F is equal to E into A into epsilon. How can you replace this epsilon? Strain. So again from strength of material, strain is nothing, delta L upon L. Delta L means what? Change in length. What is the change in length upon original length? So let's take here change in length is delta upon original length L. So in this case, what I am saying, due to the application of this force, let us take the change in length. Means let us consider the length is slightly changed, and that change in length is nothing, delta. So I am considering that as a delta. So here we can replace this epsilon by what? Delta upon L, change in length upon original length, because the original length is L here, right? So delta upon L. So your force, applied force becomes E times A into delta upon L, right? So let us rearrange the things. E into A upon L into delta. So E into A, this E into A I am considering as K. Let us take this is as, let us take K is equal to AE by L. So we can write F is equal to K into delta. You can write F is equal to K into delta. What I have done nothing, just I have taken this AE by L as K. I am representing this AE by L as K, and this K is known as stiffness. This K will be known as stiffness coefficient of element. Stiffness coefficient of element. So till here what I have done? I have done nothing. Just I have taken the relation of stress, right? Force upon area, that is external force here, because external force will be equal to the internal resisting force in this case. From there, I have drawn the equation for force. Then I have replaced this sigma by E into epsilon by using Hooke's law. And then I have replaced this sigma by delta L upon L, and I have taken delta L is as delta. So delta by L. And then from there, I have taken this A by L term as K, that is known as stiffness coefficient of element. So if you will compare this equation now, let us compare this equation. This is equation number 1, and let us take this is equation number 2. If you will compare this, what I can write, this is force. So let us write this equation in terms of force. So from here, if you will make the subject as P, so what will be that? AE by L into delta L. And this delta L we have taken as delta here, right? So P will be AE by L into delta L. So same here, F will be equal to AE by L into delta. So this AE by L is nothing, your stiffness coefficient only. This is nothing, a stiffness coefficient. So whatever I have derived here is nothing new. It is just from the strength of material, right? Now what we can do, the same bar element, if we have this equation, we have derived this equation, F is equal to K into delta. So if you remember again from the strength of material, what this equation represents what? This equation represents a spring equation. This is nothing a spring equation. So we can represent this as this spring also. Let us, this is F, and let us say this spring coefficient is nothing K. So if you will write the equation for this spring, then the equation will be same. F will be equal to K into delta, and delta is nothing, this deflection in the spring. Let us say this is delta, this is called as deflection in the spring. Deflection in the spring, right? So here you can see this bar element I have represented as a spring. We are getting the same equations, right? But the spring, this characteristics of this coefficient of a spring is given by A, E, and L of this bar element. So nothing to worry about, just use E. Whatever we are using here, we will use F is equal to K into delta. And here the most important thing is K, the stiffness coefficient of element will be nothing, AE by L. This is very, very important. This is very, very important. K will be equal to AE by L. That's it. Whatever the thing I have done here, just I am comparing the things. Whatever I have done, I have compared with the previous things what you have studied. But in this subject, what we need is this equation, F is equal to K into delta, and where K is nothing, AE by L. That's it. Remaining, you can forget the things, right? For this subject, only these two equations are known, and this is very basic things. Just we have derived also. You should know how to find out these things. Now, this is the general case, right? Whatever I have taken, this is the general case where I have derived the equation for F is equal to K into delta. Delta is nothing, displacement of the total element. So now let us take the special case, means a case where I am taking a bar element having two different forces at the both the ends. Here only one side is fixed, right? This is one side is fixed, another side having a force of F, applied force. So let's take the another case, case number 2. Case number 2. This is a bar element. Here F2. Let's take F2. This is F1. Characteristics of this is AE, and the length is again L. Again, see, this is the bar element. Why this is the bar element? Because both F1 and F2 is horizontally. acting on this element. That's why this will be considered as a bar element. A is cross-sectional area, E is Young's modulus, L is the length, and F1, F2 are the two forces acting on this element. And we know that a stiffness matrix is given by A by L. But the thing is, here if you will see, we have two forces, F2 forces and F1 forces. So we will have two stiffnesses, right? For this, we will have, let us say, K2, and for this, we will have, let us say, K1 and K2. So how will you combine this K1 and K2 to get a global stiffness matrix? What I am saying, in the previous case, there was only one force. So we got the equation for stiffness matrix as AE by L. That's it. But here two different forces are there. So two different forces, we will have two different stiffnesses, K2 and K1. But what we need to do, what is our aim? Our aim is to analyze this whole element, bar element. So somewhere we have to find the combination of this K1 and K2. So how we will find that combination of K1 and K2? We are going to see this through this case, right? So now let's say, suppose for F1, if we are going for analysis of F1, what we should do? We should fix the second. In the previous case, if you will see the previous case, what I have done, I have fixed the one side and we are analyzing for the force for other side. So we know how to analyze if one side is fixed. So same thing, same concept I am going to use in the next case also. So what I am going to do, for if we are analyzing for F2 force, I will fix the F1 side, and if we are going to analyze F1, I will fix this F2, right? So let us say this is first and second nodes. Let us check this as a node, node 1 and node 2. What is node? Already we have discussed in the introduction video, so you can go through that video. So this is node 1 and node 2. So for analysis of forces at node 1, we will fix the node 2. For analysis of forces at node 2, we will fix node 1. So let's say first case in this, what I am going to do, I am fixing the node 2. I am fixing the node 2. Here force is F1. This is 1 and 2. Let us take at node 1 the displacement is U1 and at node 2 the displacement is U2, right? So at both the points loads are acting, so displacement will be nodal displacement. We will take here nodal displacement. At every node, what are the displacement we have to calculate, right? So at node 1, let us take the displacement is U1, and at node 2, let us take the displacement is U2. Again, in the next case, what I am going to do, I am fixing node 1. I am fixing here node 1. F2. Again, same at the U2 and U1. Displacement at 1 is U1 and displacement at 2 is U2. So now considering this at node 1, we are going for node 1. We are going for node 1 now. At node 1, considering these two figures only. Let us mark this as figure number 2 and figure number 3, and this is your figure number 1. So considering figure number 2 and 3, we are going to analyze for node number 1. So from here, if from figure number 2, if you will see, we can write the equation F1 will be equal to K into U1, right? Because second here 2, the second node is fixed. See the previous case. Finally, what we got, F is equal to K into delta. Delta is what? This is the displacement, right? So already we have considered that displacement at node number 1 is U1. So for that, we can write the equation. What we can write? F is equal to K into delta. Delta here I am taking as U1. So F1 will be equal to K into U1. If you will consider the figure number 2. Now considering the figure number 3, if you are considering the figure number 3, what will be the value of F1 here? So if you will see, F1 can be written as K into here displacements. If you will see the displacements, we can write U1 minus U2. So U1 minus, right? So this is, let us check, this is for node number 1. This is node number 1. Here F1 can be written as K into U1, and here F1 can be written as K into U1 minus U2. Similarly, if you are going for F2, then in this case F2 can be written as what? K into U2, right? K into U2. K into U2. And from this figure, if you are going to find F2, then what will happen? That will be equal to K into, now here U2 is fixed, so U2 minus U1, right? See, the first term will be fixed one. Here it is fixed, U1 minus U2. In this case, here what is fixed? U2 is fixed, so U2 minus U1. That's it. Now we have this F1, F2 equations. So from there, we can say, so from here we can say F1 will be equal to KU1 minus KU2. Let us take this as equation number 1, and F2 can be written as KU2 minus KU1. Let us take this is equation number 2. F1 and F2 we have taken. See here, K into U1 minus K into U2, and if you will open this up, then F2 will be equal to K into U2 minus K into U1. Now, if you will represent this in a matrix form, how we can write? See, this, if you will represent this in a matrix form, let us take this as F1, F2 will be equal to, if you will take, see here, U1, U2 is common. So we can take U1, U2 as common. So let us take U1, U2, then a stiffness matrix. Now U1, U2 for this row, what will be the value? K into minus K, K minus K. Here again, this is U2. See, this will be plus in which term? U2. Here U1. U1 value will be minus K. So here it will be minus K. Here plus K. Right. Let's take this plus K. So if you will rearrange this, then we will get K minus K plus K into U1, U2 will be equal to F1, F2, right? Here K is the stiffness matrix, that is nothing, AE by L. A is given, L is given, AE by L. U1, U2 is the nodal displacement, F1, F2 is the nodal force. This is F1 and F2 are the nodal force. So from here, we can write, if we'll take AE by L is constant outside, then it will be 1 minus 1 minus 1 1, because if we will multiply it, we will get AE by L minus AE by L minus AE by L, AE by L, that is K minus K and K into U1, U2 will be equal to F1, F2. So this will be the final equation, where this is your K matrix, this is your delta matrix, and this is your F matrix. So K into delta is equal to F. Same equation. Equation is same, only due to the application of nodal forces and due to the nodal displacements, we got this in a matrix form. But if you will see this, then we are getting the same thing. Means the K into delta is equal to F. F is equal to K into delta. We are satisfying the first equation. Whatever the equation we have derived in the first case, see, K into delta, the same thing we are getting in this case only, but that will be in a matrix form. So let's take the next case now, case number 3. Same bar element only. But now this time what I am going to do, I am going to vary the area of cross section. These all things we have discussed in the first lecture, how to take the nodes, how to select the nodes, sudden change in area, uh, point where the load is acting, right? So these things, just go through the first video, that will be helpful. So what I am going to take this in this case for a stepped 2-bar element. Stepped 2-bar element. So in this case, we have combination of 2-bar element, but that is a step. A step means there will be sudden change in area. So let's take that condition. This is bar number 1. Now this is second bar. This is bar number 1. This is bar number 2. This is fixed one. Here area is A1. Young's modulus, let us say E1. Here area of cross section A2, E2. Length I am taking this as L1 and this is L2. If you will see the nodes, so this is, let us take, this is node number 1. Here sudden change in area, so we have to take the node. So this is node number 2 and this is the third node, because this is the end. At ends we have to select the node. In between also I am going to select this second node, because here the change in area is there, sudden change in area. So whenever the sudden change in area, we have to select node at that point. So this is the second node. So in this case, how you are going to develop the stiffness matrix? What the equation you are going to get for the stiffness matrix? 3 cases. First, in very simple case. Second case, on both sides we are applying the force. Third case, step 2-bar. Only 3 cases are there. If you know that these 3 cases, it will be very, very helpful for you solving the problems. Rather, I can say, if you know these 3 cases, you will be able to solve all the problems regarding this bar element. Nothing will be left. So simply what I am going to do for easy analysis, what I am going to do, we know we can replace a bar by a spring. So let us take, this is the spring number 1, this is a spring number 2, and this is, let us say, K1 and this is K2. We know this. That is why I have discussed in the previous first case, we can replace this bar element as a string, because the equation we are getting will be same. So here K1 and K2, we are replacing this as a K1 and K2. So here what will be the value of K1? If you will see, what we will get the value of K1. We will get the value of K1 as A1 E1 by L1, right? AE by L. So A1 E1 by L1. K2 value we will get A2 E2 by L2, right? So this is K1 and K2 value. Now, if you will see this, if you will draw the FBD, free body diagram of this bar elements, what is going to happen? Let us take this first one. This is node number 1. This is node number 2. So what is going to happen? Here, let us say this is F2. And here, let us say F1. For second and third node, let us say this is node number 2, node number 3. Don't consider the area of cross section. Area of cross section of second and third will be less than this, but due to the exaggerated thing I am showing here for second and third. So for second, again, this will be F2 and this will be your F3, right? So this we will call it as element 1, because here 2 different elements are there, 2 bar elements are there, right? So element 1 and this is your element number 2. So if you will see the individually, if you are going to see individually, then what you are going to get, see, this case is already we have discussed in the previous case, this type of, see, already we have discussed, right? We have got the equation also. So what I am going to do, I am directly going to use this equation in this case, because see, F1, F2, AE by L, so we got this equation. So same I am going to use here for element number 1 and for element number 2. So directly I am going to write the equation, that will be F1 will be equal to K1 U1 minus K2 U2. You will say, sir, why you are using this F1 here? Why you are taking it displacement as u1, u2. This is u2, and again this is u3. So, okay, here it is fixed. Fixed means this displacement. So later on, after deriving the things, we will make it as 0. Here I am considering that. Why I am considering? To make this derivation easy. At last, if this is fixed one, so we can keep u1 as 0. So we will get the things right? So f1 is equal to k1 u1 minus k2 u2. Already in the previous case, just go through the previous case. From there, I am directly writing the equation. F2 will be minus k1 u1 plus k2 u2, right? So this is for which element? I am going for this. This is for element 1. Element number 1. Because in element 1, we have F1 and F2. So directly we can write, I am going to write directly F1, F2 will be equal to K1 minus K1 minus K1 into U1, U2. Let us take this as equation number 1. This will be the equation, and this will be the final result. From where I got final result. See, this is the final result only. See? So for first element K1, 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 remaining things will be same. So directly I have written here. Now next, for element number 2. For element 2. So for element 2, what will be the equation? For element 2, 2 means second node and third node. So we have to write the equation for F2, and we have to write the equation for F3. F2 will be equal to K2 U2 minus K2 U3. Displacement, nodal displacement U2 and U3 we have to take. For K3, we can write minus K2 U2 plus K2 U3. This will be the equation. From here, what we are going to get the matrix F1, sorry, F2 is, sorry, that will be F2 and F3. This F2 and F3 will be equal to K matrix. K matrix will be again K2 minus K2 minus K2 and K2 into U2 and U3. Let us take, this is equation number 2. Now from equation number 1 and 2, if you will combine the equation number 1 and 2, what we are going to get? Adding equation 1 and 2. Adding equation 1 and 2 means, rather we can say combining. Anything you can say, combining equation 1 and 2 or adding equation 1 and 2. What we are going to get? Total forces are F1, F2 and F3, right? So we will write F1, F2, F3. Is equal to. Now a stiffness matrix. See, stiffness matrix first. So this is, before writing the stiffness matrix, let us take the displacement. Displacement is R of U1, U2, U3. Now how will you combine? So here what you will write, if you will write anything, then what will be that? Suppose this is anything, a stiffness into U1 will be equal to F1. So whatever the you are going to write, that will be equal to F1 only. So F1, where is F1? In this case, F1 is there? No. So where is F1? F1 is in previous equation here. So in F1, what we are seeing, this stiffness is K1 minus K1, right? So let us take K1 minus K1. K1 minus K1. With respect to U3, any stiffness matrix for F1, see the previous case. K1 is with U1, right? And minus K1 is with U2. But U3 is there. In this case, U3 is not there. Means if with respect to U3, this K1 is nothing, 0 for force F1. So we will write here 0. Try to understand this very carefully, because this will be helpful in doing problems also, because in problems also, here we are combining for with k1 minus k1 and all. There also you have to combine with using that numeric values. In that we will calculate the numeric values AE by L, and then we will combine the stiffness matrix. We will calculate a stiffness matrix for element 1, we will calculate a stiffness matrix for element number 2, and then finally we will combine that stiffness matrix. So in this case also we are doing the same. For element 1 we are writing the stiffness matrix, for element 2 we have written the stiffness matrix, and we are going to combine that stiffness matrix to get a global stiffness matrix. Global stiffness matrix means overall stiffness matrix of a combined element, because in this we have two elements. We have a one bar element, but that bar element, if you will see, we can divide into two different elements, because that element is divided by a node at between, right, in between. So here k1 minus k1 0. Now coming to f2. F2, if you will see, this is very, very important, because again f3, coming to f3, let us write f3 first. Coming to f3, is there any f3? No. In this equation, f3 is there? Yes. f3 is for only, see, minus k2 for u2, my k2 for u3. For u1, is there any u1 term? No. Means for u1 term, this stiffness matrix should be 0. So we can write here 0, and then we can write minus k2, and then we can write k2. Now the main thing is to write the stiffness matrix here for f2, because if you will see this f2 is in equation number 2 also, and f2 is in equation number 1 also. So how you are going to write for f2? So before writing that, you have to see the displacement u1 u2, and again here u2 u3. So u1 and u3 is independent, right? There is no repetition of u1 and u2 in this equation. In equation 1, u1 u2. In equation number, let's see here, u1 u2, and again we have u2 u3. So if you will see, u1 and u3 is not repeated, means whatever the thing is there for u1 and u3, we can write it directly. So for f2 u3, what is u3 value? Minus k2 into u3 will be there. Just multiplication. If you will multiply for f2, what will happen? k2 into u2 minus k2 into u3. So for u3, what is the stiffness value? Minus k2. So we can write here minus k2 for u3. So minus k2. Now if you will go in first equation, then we will go for f2 u1. So for u1, what is this? Minus k1. So directly we can write minus k1. So minus k1. Now coming to f2 u2. So here also u2 is there. Here also u2 is there. So in this case for u2, in terms of f2, what is the stiffness? K1. Remember this. This is K1. And in this case, for u2, for f2, what is the K2? So obviously, in equation 1, we have for this K1, and for this we have K2. So what we need to do? We have to add these two. So we can write here K1 plus K1 plus K2. This is very, very important. If you will make mistake here, then your whole problem will go wrong. So that is very, very important. When you are going to combine the stiffness matrix, just remember the things, how to combine, because remaining things are all okay. Just you will see where is u1, u3. If we have two noded, three noded, then two elements, obviously number of nodes and number of elements. If number of node is 5, elements will be 4, right? So here 3 nodes are there, 2 elements. 2 elements means u1, and 3 nodes means u1, u2, u3. u2 will be in between. So you will share a stiffness with element number 1 and a stiffness with element number 2 also. Coming to u1 and u3, that will be independent. That will depend upon only one element. u1 will depend upon element number 1. u3 will depend upon element number 2. But u2 will depend upon both. So that you should remember, this is the final stiffness matrix. This stiffness matrix is nothing, that is called as global stiffness matrix. global stiffness matrix. Why we are calling it global stiffness matrix? Because this stiffness matrix represents the whole element, the whole bar element. This stiffness matrix represents this element, right? But this stiffness matrix represents only this portion, right? That's why it is. This is called as local stiffness matrix. If you will see, this is called as local stiffness matrix. This is local stiffness matrix. This is also your local stiffness matrix. Local stiffness matrix, but this is your global stiffness matrix. This is delta, right? Delta matrix. This is called as your global displacement vector. Global displacement vector. This is called as global displacement, and this will be local displacement vector. This is called as global force vector. Force vector. This is called as global force vector. So global force vector is nothing. F is equal to K into delta, where this F is nothing your global force vector, K is global stiffness matrix, delta is global displacement vector. We can represent this because this is F matrix, this is K matrix, this is your delta matrix. So again, finally, we are getting the same thing. F is equal to K into delta, but here F meaning something else. F meaning global force vector. That will be all the forces. K is global stiffness matrix and delta is global displacement vector. So this is the final result we got, the combination of all the stiffnesses. If 3 elements are there, then also you can add, but they won't ask the 3 elements problem. Generally, they are going for 2 elements only, because 3 elements calculation will be very, very lengthier and combination will be slightly lengthy, right? Now coming to the initial case that I have told you, that in this case, here I have taken the fixed support, right? So in this case, if I have taken the fixed support, what does it mean? It means the displacement at node number 1 is 0. There will be no displacement, because if something is fixed, there should not, fixed support means what? It won't allow the element to either displace in x direction, y direction, or even rotation also, moment also. So the displacement will be 0. Second thing, here F2, if you will see this F2 value, I have not given any force value here, F2. So F2 is also 0. F3, let us say this F3 as P. What I have taken? F3 as P. I have applied a load vector here, load here, P vector. So if you will see the boundary condition, these are called as boundary conditions. So if you will see the boundary condition, what is boundary condition here? Boundary condition is U1 is equal to 0. Why? Because fixed support is fixed. F2 is equal to 0 because no load given. No load given at that second. No load given on second node. That's why F2 will be 0. And F3 value is equal to P. Now here also one thing you have to see, P is in positive x direction or negative x direction. Positive x, then P, and if it will be in negative x direction, suppose I am taking in this direction, then you have to take, in place of P, we have to take minus P. That you have to consider, directions you have to consider in this case, P. So now if you will see this, then what is going to happen? See, this is very, very important. You just understand this thing. This is really very, 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 very important. So here, if I am going to remove this U1 as 0, this F2 value is equal to 0, right? And F3 value is going to be P. So now in this thing, understand one thing, whatever the value is 0, no problem. If any value related to displacement is 0, listen very carefully. Others values are 0, no problem. But if any value related to displacement is 0, then what we will do, we will remove whole this. If you are going to see this u1 is 0. If u1 is 0, then we are going to remove this line. We are going to remove this row. Just remove this row, right? And this one, because this is for u1, this is for u2, and this is for u3. So u1 value already you have done 0. So if u1 is 0, remove the row, whole row, and column in the stiffness matrix related to that. Suppose u2 will be 0, then we will remove this middle one. If u3 will be 0, then we will remove this third one, third column. Third column for whole stiffness means in from F1 also, from displacement matrix also, from stiffness matrix also, from load vector matrix also. But if you will see this removal of column, that will be from only stiffness matrix. Suppose u1, u2, u3 are there. So first column will be for u1, second will be u2, third will be u3. So if u1 is 0, remove one, first one. If u2 is 0, remove second one. If u3 is 0, remove third one. So if you have removed this, then what we have, the final matrix. See, now we have final matrix, this one. Only two forces, right? Here, this is your stiffness matrix and this is your displacement matrix. So just we will write it again. So it is nothing. F2 is value 0, 0. F3 is P is equal to stiffness matrix. What is stiffness matrix? K1 plus K2, because already we have removed this. These all terms you have to remove. So K1 plus K2 minus K2, K1 plus K2, which is minus K2. Then here minus K2 and K2, minus K2 and K2 into displacement. In displacement U1 is 0, then automatically we have U2 and U3. So U2 and U3. This is your final result, final relation. Final relation. After applying boundary condition. After applying boundary condition. This is the final result after applying boundary condition. Now you have 2 by 2 matrix, that is easy to solve. So if you are having 3 elements also, don't worry, they will give such situation. In that situation, suppose u1 and u4 will become 0, then finally you are going to get 2 by 2 matrix. Then easy solving purpose, it will be easy, because in examination they are not going to ask you to solve 4 by 4 matrix. That will be very, very difficult and lengthy process, and you will not get such time to solve the problem. So in paper, what they will give, suppose they are giving 3 elements also like this. Suppose if they will give 3 elements also like this, then what they are going to do, they are going to fix 2 sides. So what is now u1 0, this is u2, u3, and u4 is equal to 0. If 2 displacements are 0, so what will be the size of matrix? Finally, you have to solve 2 by 2. See, this type of matrix you are going to get in terms of u2 and u3, because third and fourth is 0. So total you will get 4 by 4 matrix, but that will be reduced to 2 by 2 matrix. So solving will become easy. So by seeing the problem, don't be scared. Oh, 3 elements are there, 4 elements are there. No problem. Even 5 elements are there also, 3 elements. They will give such situation that they, or suppose they are giving 4 elements. Then what do they will say? They will say, let us take one more example. Suppose they have given such type of element. This is u1, u2, u3, u4, and u5. So they have given u5 0, u1 0, and in between the constraints, something they will give that considering u2 is also 0, means displacement at second node is also 0. Then again you are left with only u3 and u4. So finally result will be of 2 by 2 matrix only. So finally you have to solve for 2 by 2 matrix. Hardly 3 by 3, that is very, very rare case, but most probably 2 by 2 only you are going to solve, whatever be the number of elements, right? So this is all about the stiffness matrix of the bar element. In the next class, we will see the problems on these bar elements, how to solve So you have to see the three cases. First case is very simple case, that is directly we can say that strength of material case, then second case, and then third one. Third one is very important because that is the combination of all the things. So third one is very important, but you should know how to find these things. Okay. So thank you. We will continue the class.